So isomerization is common in coordination compounds. Isomers are compounds that have the same chemical formula, but they have different arrangements of the atoms. So we can break isomers into two broad categories. We can look at those that are structural, come on pointer, where the atoms are connected differently. Or we can look at stereoisomers, where the atoms have the same connectivities, but they are arranged differently in space, okay? And these are the sorts of things that you're gonna see if you go on to organic chemistry, these different types of isomers, except they won't involve metals. So if we look at structural isomers, we find we can have coordination isomers or linkage isomers. In a coordination isomer, the ligand and the counterion exchange places. So you could have, I can't think of an example because my brain isn't working, but the ligand and the counterion may be exchanged in the two different compounds. The chemical formula, the molar mass, is the same, but in one of them, say the chloride is a counterion, in another one it's one of the linkage isomers. And so that will affect some of its properties. Another type of isomer that's structural is a linkage isomer, and here we have the same ligands on the metal ion, but they're coordinated in different ways. We're going to go over all of these in more detail. Stereoisomers, we can have geometric isomers where the ligands have different spatial arrangements around the metal ion. And so we can look at cis-trans, or I'm never sure how to pronounce that. Fac-Mer or Fac-Mer. Which one should we go with? Fas or Fac? Let's do Fas. Yeah, that has less issues, potentially. So Fac-Mer isomers, we'll talk about what those are. We can also have optical isomers. And here, these are two compounds where they are mirror images of each other, but the mirror images are not superimposable. So let's talk about the structural isomers. The coordination isomer, you've got coordinated ligand exchanging places with an uncoordinated counterion. So these are complex ions, right? So there has to be a counterion. You can't have a beaker with just chloride ions in it, right? You may only care about the chloride ions, but there has to be something else like sodium or potassium to balance the charge. So all of these these complex ions have counterions. So here we have, do we want to try to name that? We can try. I don't know. Okay, so NH3 doesn't have a charge, right? And bromine has a -1 charge, and chlorine has a -1 charge. So what's the charge on the cobalt? +2, right? So NH3 we call amine, and this is bromo, right? So amine comes before bromo in the alphabet, and we use this number 5 is penta. So pentaamine, bromo, cobalt 2 chloride, right? Over here, the difference is that now the chlorine is one of the ligands, and the bromide is the counterion, okay? So you've got this solid, the molar mass is the same, the simple chemical formula is the same, but the compounds are not exactly the same. So this would be pentaamine chlorocobalt 2 bromide, right? You see the difference? Yes?
Do you always put the element outside of the brackets last when naming?
You name the cation first and then the anion. And so inside the brackets is the complex ion. So I think it's possible to have a negative complex ion. But you name the first ion first and the second ion second. Good question. Linkage isomers, here we have the same ligands, but they're coordinated differently. So some ligands, like the nitrite ion, has more than one lone pair, and so it can attach to that metal ion with its coordinate covalent bond using either the nitrogen atom or an oxygen atom. So if it attaches by the nitrogen, we call it nitro. If it attaches by the oxygen, we write it this way to indicate that it's the oxygen, and we call it nitrito. So just remember, the exam on this is a take-home exam, right? So we don't have to memorize all of these things. We just need to know they exist so we can go look them up and get them straight. So here are two linkage isomers. So pentaamine nitro-cobalt 3. So here's our cobalt, here's our 5 ammonias, and we write it NO2. This is sort of a yellow-orange color. Pentaamine nitrito-cobalt 3, we write it ONO to indicate that the oxygen is bonded to the cobalt, and this has a different color. It's a red-orange color. So here the oxygen is bonded to the cobalt, here the nitrogen is bonded to the cobalt. That's different, right? It's not a big difference, but it is different, right? So here's that nitrito where we bond to the oxygen, and nitro is bound to the nitrogen. A couple other isomers or ligands that can do this. The cyanide ion, it's called cyano if it bonds on the carbon, isocyano if it bonds on the nitrogen. Here we've got, this one's called cyanato or cyanato and isocyanato, and then we've got thiocyanato and isothiocyanate. This prefix thio refers to sulfur, and it's often used when sulfur takes the place of an oxygen. Again, aren't we glad we don't have to memorize these? I don't have them memorized. Okay, geometric isomers. The ligands are bonded in the same way, but they're arranged differently in space. And we touched on this a little bit in Chem 1A when we looked at some double bonds. So we can have cis-trans isomers. So here we have square planar complexes where we've got a metal ion and there's 4 ligands, 2 of one kind, 2 of another kind. It's square planar because there's a lone pair up here and a lone pair down there, essentially. And so we can have the 2 chlorines on the same side and the 2 amine groups on the same side, and that's called cis. And here we look at the amines are on opposite sides of the cobalt and the chlorines are on opposite sides of the cobalt, and that's called trans. So cis and trans are things that you should learn, because if you take OChem, you're going to use them a lot. So trans means across. Think of the Trans-American Railroad, right? It goes across America, right? Cis, I think of sisters. Sisters, unless you had a really horrible relationship with your sister, if you were being picked on by a bully, hopefully your sister would be on your side, right? You'd be on the same side. So here we have like ligands on the same side. Here we have like ligands on opposite sides. So this can happen when we have the general formula, a metal, 2 of one ligand, 2 of another ligand. It can also occur in octahedral complexes where we have 2 ligands the same and then 4 ligands of a different type. So here Again, this is we can look at this occurring in the equatorial positions here, where here we have the two chlorines next to each other, adjacent on the same side, and here they're on opposite sides. So this is trans, and this is cis. Now, another geometry that has 4 is a tetrahedron, right? But you can't have cis-trans isomers in a tetrahedron because the 4 corners are spaced evenly, and no matter what combination you try to put together, those two things that are different are always next to each other. There's no opposite side. So you can't have cis-trans isomers in tetrahedral complexes. Fac-Mer isomerism occurs in octahedral complexes with the general formula shown here, where you have 3 of one ligand and 3 of another ligand. So this would be, let's see, this is it doesn't give a charge, so this must be cobalt 3. It would be triamine trichloro cobalt 3. So we can put these chlorine ligands here where they form a triangle. They are essentially on the face of the octahedron. They comprise one face of the octahedron. So the octahedron has triangular faces. Can you see that at all? So here the 3 chlorines are occupying the corners of one face. Here they are not. Fast stands for facial isomer. They make up one face. This MER stands for meridian. And in terms of geography, what does meridian mean? It's a line around the globe, right? And so here, they're occupying 3 spaces in a plane going around, right? Does that make sense? They form an arc around the middle. So this is the MER isomer, that's the Fac isomer. Any questions? So draw the structures and label the type of all the isomers of each complex ion. We've got to have some spatial visualization here, okay? So here we've got, let's practice naming that guy. First we have to figure out the charge on the chromium. The water has no charge. The chlorine has a -1, so a total of -3. Yeah, so this must be +4, right? So that's going to be triaqua, trichloro, chromium 4. When the complex ion, the question is the metal always last? When the complex ion is a cation, well, actually, yes, it's always it's always last in naming the complex ion. If it's a negative ion like this, then we don't say cobalt, we say cobaltate. Yeah, but it's still last. Okay, so we look at this, we have 3 waters and 3 chlorines. So 3 and 3, that's a total of 6. So this is going to make an octahedral shape. Instead of trying to draw all of the atoms. Let's just use balls for the metal and for the ligands, right? And then we can identify what those are. So this is going to have an octahedral shape. So we've got something in the middle, and we've got this one coming out. We got this one coming out, and then we've got something going back there, something going back there, something going straight up and down, and something going straight up and down. So let's say that the H2O is blue and the chlorine is green. So for the first isomer, you can just color them however you want. And so like this one and this one and this one. And then make these blue. So we can look at the chlorines or we can look at the waters. It doesn't matter. Are these occupying the face of the octahedron, or are they in an arc around the middle? Face. So this is the Fac isomer. And then we have to see if there are other possibilities, which of course there are. So what we want to do here is to make it easier to look at, let's not move everything. Let's just move one of the chlorines. So I'm going to keep this one the same and this one the same. And I'm just going to change this one. So I've got 3 different places that I could put it. If I put it on this one in the back, I'm still going to have a facial isomer, right? And so, yeah, it might look different when I draw it, but really it's just twisting it in space. So I don't want to put it over there. If I put it down here, then I'll have a meridian. So let's go ahead and do that. I'll put it down there and make these the waters. And so this is the Mer isomer, because these are forming an arc around the ion in the middle, the metal. Do you see it? It's really easy for some people to see, and it's really hard for other people to see. It's just how your brain works. If it's not coming to you, there are some really cool simulations available online, and we can pull those up and look at those, and then you can actually spin them in space, and that can really help with you visualizing it. Usually once you get the idea of what this is supposed to represent, then you can imagine the picture and everything's good. So any questions about that one? So here we have, oh yeah.
Is it like if they're all next to each other, then they're going to form a face?
Well, if they're all next to each other, then we have to ask, what do you mean by next to each other?
In a line, all like.
So here, this one is next to this one, and this one is next to that one, but this one is across from that one. So these are making an arc. If we connected these, they'd make a semicircle. They could go around. If they included this one, it would be around like an equator but tipped on its end. Here, if we connect these, we're going to get a triangle. And then that defines the face of one of the faces of the octahedron. Does that make sense?
Yeah.
So let's look at this one. this has 5 isomers. So what shape is that going to be overall? I'm sorry, not 5 isomers, 5 ligands. Vesper theory. 5 electron groups, 5 balloons. What shape do they make? You tie them together. Trigonal bipyramid. That's okay. So, trigonal bipyramid, we got one up and down. We've got one coming out to the right. Then there's one going to the back and one coming out here. So these 3 are around the middle. Those are in the equatorial position, like around the equator of the Earth. And this one's at the North Pole, and this one's at the South Pole. Those are the axial positions. So now we have these 5 ligands. We have to stick them in. So let's use green again to represent chlorine. And I'll use red to represent oxalate. And we'll let the ammonia be blue. So we have 2 ammonias. So I'm going to stick them in like that. Just, kind of stick them wherever you want to, really. And then we have 1 of the oxalate. I see a problem here. Something I overlooked. What kind of a ligand is oxalate? So there's oxalate. Do you see all those lone pairs? Oxalate is a bidentate ligand. So it's going to attach in 2 places. Easy to overlook, right? I just overlooked it. So if the oxalate binds in 2 positions, that means we don't have a trigonal bipyramid. We have an octahedron. So we have to alter the drawing here. So we'll make an octahedron instead. So what we'll do with the oxalate is going to be, it's going to occupy 2 places. Now those 2 places have to be next to each other, because oxalate is not big enough that it can stretch from one end to the other. That's not possible. They have to be right next to each other. Okay? Okay, so now that we fixed that, I've got my ammonias in there, and I'll stick the chlorines over here. So let's draw another one of those. That didn't come out very well either. A triangle. There we go. So let's leave the oxalate where it is. That seems like a good idea. So there's the oxalate. what we want to do here is we just want to switch two. Switching two chlorines isn't going to change anything, so let's change this chlorine with that ammonia. So I still have the ammonia down here, but I'm going to put the other one there. And I had the chlorine here, the same as it was before, and I have a chlorine up there. Aren't these pretty? So, these are geometric isomers. How do we name them? Well, Fac and Mer aren't going to work, right? Because we don't have three of the same, so we can't have one that defines a phase. So it must be cis and trans, which is on the same side and on opposite sides. So if we look at chlorine, here the chlorines are next to each other as close as they can be. And here the chlorines are also next to each other as close as they can be. Here the ammonia molecules are opposite each other, and here they are close together. So what's the first one? Trans. And the second one is cis. Yeah, you just need to go with the one that's different. The oxalate's always going to be the same. And here we see the chlorines are the same, and so that's not going to help us out at all. But the ammonias are different. Now, if the ammonias were also the same, then you have to consider that maybe my second isomer is actually identical to my first isomer. And I didn't actually draw two isomers. That can happen very easily. It's very helpful to use a model kit, or even things like gumdrops and toothpicks, or mini marshmallows and toothpicks, and actually build something. And then you can build one and build another, and then you can turn them around and see if they're actually the same or not. Any questions? That's a glitch in how the program works, that we went all the way back there. Oops. Okay. So optical isomers are non-superimposable mirror images of each other. And such molecules are called chiral. Chiral molecules exhibit optical isomerization. So these two isomers are called enantiomers. They exhibit optical activity, and the optical activity is how this was first discovered. So if you have two solutions, this was first discovered with sugars. If you have two solutions, one of each optical isomer, and you pass polarized light through the solutions, the one isomer will bend the light to the left, and the other isomer will bend the light to the right. It's really kind of crazy. So we're not going to worry about how these bend light, but that's why it's called optical activity. So we can have optical isomers with, yeah, I lost that sentence. We can have optical isomers with complex ions. You can have optical isomers with tetrahedral complexes, but it can only happen if all four of those coordination sites are occupied by different ligands. What we have here is an example of optical isomer where we have three bidentate ligands. So here we're asked to determine whether the Fac or Mer isomers of, let's see, triaqua trichlorochromium 4. Yeah. We're just practicing. Are optically active. Okay. So we need to draw the isomers. So we've got 6 ligands, and so this is going to be this octahedron again. So let's make H2O blue and chlorine green. So on the first one, I'm just gonna, oops, not that. I'll make 3 of these green. And 3 blue. So, is that the Fac or the Mer isomer? Yeah. It's the Fac isomer because these 3 chlorines form one of the faces of the octahedron. The 3 water molecules also form a face of the octahedron. So let's make a Mer isomer. Let me do it this way. So the blue ones are going around the middle, right? And then I'm going to put the green ones in the remaining places. So this is the Mer isomer. Now, we should also consider whether there are any other variations of this. So, what could we do? So I kept these 2 the same, and I switched these 2. If I switch those 2 instead, I'd have the same thing. I think those are the only 2 options. The way the question is asked, Fac or Mer are optically active. Oh no, okay. So it's asking, is this isomer optically active? Is this isomer optically active? So in order for it to be optically active, the mirror image has to be a different molecule. So one way to do that is to draw the mirror image. So the mirror image, these 2 closest to the mirror and this one over there are blue. And this one, and that one, and this one over here are green. So then you have to imagine taking this one, can you rotate it such that it could be superimposed on this one? Yes, you can. Not optically active. The mirror image is the same molecule. Okay? And then this other one, I didn't really leave much space, but this one, and this one. So can I take this isomer, this molecule, and rotate it in any way and cause it to be the same as this? Yeah, you can. You see it?
Yeah.
Okay. So this one also not. So neither is optically active.